Well, Stan, I know you're American, and yet you grew up in Poland. So how did that happen?
Well, I hadn't found myself there in about 1922, I think it was, when my parents left States and we settled in Poland, in the western part of Poland, and became farmers first. And then we started growing up, where the time was to go to school. So you had to change to go to the place the schools were in. In this case was a small town called Pleszew, old town, established sometimes in 1000, more maybe long ago. And that's what I started going to school to learn a few things, which finally ended in 1939 with my entering the higher education, learning of higher education. That means the technical university in Lwów, which today is known as Lviv. I still like to call it Lwów. And after that, in 1947, I got my diploma engineer's license and came to States.
Okay, well, there were some interesting things happening in that part of the world between the late 30s and 40s. So tell me about how did that impact you?
Well, I changed names a few times, but
and why did you do that?
Well, you don't want to be on list. You see, if there is no paper trail, they cannot find you, can they? In other words, if how the Germans operated. Well, first they promise you that if you want to live and buy food, you should have what they call Kartenspeisen, that is coupons to buy food. Well, if you wanted to get coupons, your name appeared someplace. Now, if you didn't want to have coupons, they didn't know that you exist. And if they don't know that you exist, you can survive.
Okay.
It's very logical, isn't it?
Well, you told me one time a story about tanning leather. What did that involve?
Oh, well, the problem you see during the war, there are shortages of everything. You cannot buy soap, you cannot buy leather, you cannot do so you have to manage to do it somehow. And one of my activities was to provide leather for people who need it. And in other words, now the problem was again the same thing. Normally, in those days, if you wanted to prepare leather from, I don't know how to call it,
hide or
hide,
yeah.
Then it took about, sometimes about 2 months. And of course, during the war, you cannot afford it, so you have to shorten that time. And I was able to do that in about 3 days. And that way, of course, you buy the stuff, you make it, and you sell it, and that's about it. But you have to do everything fast. If you do it slowly, then the chances of you being caught are much greater.
And that's a very smelly process, I believe, isn't it?
No, not the way I did it. No. Normally it is a smelly process, yes. Especially the first one when you try to remove the hair. That is not very pleasant. But after that, depending what kind of tanning procedure you use. If you use the old-fashioned, that it takes 6 weeks or more. If you do use perchromate or dichromate, then it takes perhaps a day.
Okay, so how did you know to do this? Is this something you learned in school and how to tan leather?
No, that's something which, well, I really don't know how I came. Probably bought the book. Oh yes, I bought the book in German, which was all about the art of making it. And so you learn it and do it.
They didn't have the internet then, did they? They didn't have the internet then.
No, they didn't have the internet. But one good thing was that you could buy books from Germany. There was no restriction on that.
Okay.
So,
and the SS troops, were they the ones that were out looking to try and determine if they found your leather, they would have used it for themselves? Is that?
Well, no, that wouldn't be as jobs. No, they didn't bother with this. That was most likely the local police.
Okay.
Those the so-called collaborators, those who were forced to escape to Germany after the war was over.
Okay.
So
then you moved back to the United States.
Yeah,
when was
I came
that?
back to the United States and lost about 10 years of my productive life doing nothing. Really something which, when I was working at GE, well, maybe the last couple of years was then I had to use my brain. Before that was just routine things which could be done by anybody.
Okay.
And the pay was lousy and everything else.
So then someone hired you to move to San Diego and work for the Navy?
No, that was still something different.
Okay.
In between, about, what was it, 1956, I decided that, why don't I get another degree?
Okay.
So I went to, and then there was a choice to make. Well, you could take any school, you could take RPI in Troy. No, it wasn't. So I decided, at that time they had an opening in Philadelphia, that means GE. So I transferred to Philadelphia and enrolled in the University of Pennsylvania, which is one of the so-called Ivy League schools, if that has any. And after a couple of years, I finally got the PhD, the degree, which presumably gives you some advantages. Well, perhaps it does. Mm-hmm. And after that, I had a very brief period at SRI, from SRI to Lockheed, from Lockheed to the Navy in Corona. From that, then the rest of the story, you know. Okay.
So, when you started working for the Navy in San Diego, you were doing work developing batteries, is that right?
Well, actually, I wasn't developing batteries. My start was a kind of electrochemical research rather than batteries, although the main thrust was batteries, that is quite true. But my activities were not in batteries. For some reason, I got to know the gentleman in Naval, Dr. Miller. I don't know what you remember him. Well, he was I don't know what his position was, but in any event, he had access to the better restaurant, so it had to be on some higher level. Mm-hmm. And my first assignment was actually to devise for him research programs in energy, electrochemical energy type thing. And well, at that time he of course lost the ONR money, because ONR decided they are going to supervise, to control the research in well, and the rest is of course, you know. Then I came here to San Diego, and here problem again with this propulsion and all that stuff.
Okay, so you had actually encountered Martin Fleischmann before 1989. Why don't you tell us about that?
I met him in the Boston in the pub there. The first thing we had was a martini, if I remember correctly. He came. He was supported by ONR, and there was an ONR review in Cambridge, Massachusetts, and we ran into each other there. A very interesting fellow.
Okay,
when was that?
Yeah. Do you know about when that was?
Pardon?
About when was that?
Probably about 72, something around that.
Something in 1970, 1972, something in there. Okay. So that was quite a while before the 1989 announcement.
Oh yes, well, I met him later on because he was still supported by ONR, and I had a connection with Jerry Smith,
Mm-hmm.
so we ran into each other. And then, of course, once he came to, when was, I think in November '88, I think was the time in which he and Pans proposed to DOE.
Mm-hmm.
And I think this problem of review, they sent for review to Jones.
Mm-hmm.
You know the story.
Yes.
Now, the problem is this. It seems to me that the asking for so-called peer review only makes sense if whoever makes the proposal is unknown quantity.
Mm-hmm.
But it seems to me that asking a fellow like Flashman, who proposed a problem, to have somebody review his proposal, it seems to be rather odd.
It'd be like me reviewing a proposal by Einstein, something like that.
Kind of.
Okay, so you knew Martin Flashman, and did you know what he was working on? Did you know that he was working on the...
I knew only that something unusual is going to be announced soon.
Okay.
And of course, after March 23rd, '89, we knew what that thing was.
Okay, so when he announced that, a lot of people ran to their labs to try and duplicate it, and we did something similar. You went to the lab too.
No, I did
days,
not.
didn't you?
That was the other people who went.
Okay.
And the same evening started experiments. No, my problem was, remember, it was a little bit differently. What I was thinking was this. I was listening to what people were doing,
Mm-hmm.
and asking myself, why do we have to wait so long? Why not to change something?
Okay.
And to change something was late. Why don't we co-deposit? That means, you know, the process in which you co-deposit palladium and evolve deuterium at the same time. What you are doing, you are eliminating the whole process of waiting until the complete saturation is achieved, and then the incubation period and so on. So that was the idea. Let's do co-deposition and see whether we will get the same results or not. Well, it turned out that we not only got the same results, but got them without any delay. That means we could start the experiments today and end it today if we wanted to get information whatever we wanted.
So just like when you were developing techniques to reduce the time to tan leather, you developed a technique to cut the time to experiment in the cold fusion.
Pretty much.
Pretty much. The early experiments, I think what you did was you co-deposited. Isn't that's actually kind of an electroplating process, isn't it? Or,
that's precise.
And,
that's what it is, yeah.
Or chrome plating. It might be, people talk about chrome plating and things like that. But it's different elements, but basically it's the same thing.
Yes, essentially it's the same thing, sure.
You have, in this case, you had the palladium metal dissolved in the solution.
Yes, what if you're looking for analog, would be brass plating, in which you plate copper and zinc together.
Okay. Only in this case,
what you are doing, you are plating copper, palladium, and deuterium.
Okay. And so the deuterium is evolving and loading up the palladium at the same time. Immediately.
Yeah.
And in the early experiments, about all you did was you put a thermistor on the back of the electrode.
Well,
and what were the results of those experiments?
Well, you have to remember one thing, that first you do a very qualitative type of experiment to see do we have the same effect or not. Now, Flashman claims that the signature of his experiment was extra heat production, something in excess of what one would expect. Then, of course, where that heat would be coming from, it had to come from the palladium deuterium alloy. So one way of doing that would be put a thermistor or thermocouple or whatever to see whether there is a heating effect connected with it. Of course, we have seen almost within 15 minutes the difference was about 2 degrees to centigrade between the solution temperature and the electrode temperature. That would indicate quite clearly that there is where the heat source originate.
So with that first experiment, you addressed one of the primary criticisms of the skeptics, and that was that the heating was actually
Coming out of, yes.
out of the solution, ohmic heating in the solution.
Yeah.
You can go into that a little bit more for the layperson.
Yeah. Can you explain a little bit more about that? How, why is that important? Why wouldn't the electrode just heat up the same way?
Which would be much more accurate.
What I want to talk about is there's more resistance in the solution than in the electrode.
Of course, yes.
Okay, so can you explain that? Explain how that.
Well, normally the resistivity of solution is much higher than metal. So if you wanted to claim or suggest that this is normal heating, one could simply say, well, then the heating would have to come in a solution, not because that's what the resistance is higher. Well, we don't see that. We see the opposite. That means, and since we do know that the resistivity of metal is less, then any heat produced there is not the Joule heating, the R square heating, but something else. Now, what is that something else? That the story will evolve.
Okay, so it's kind of like your toaster. You've got a normal plug and copper wire that comes up to the toaster, and then you've got a high resistance nichrome wire or something that runs in the area where you want the toast, and when you pass the current through, since that's higher resistance, that's the part that heats up.
Yeah.
And in this
Not
case, and in this case, the solution is the higher resistance, so it should have heated up.
Yeah, and it's not, okay.
Okay, so now that you knew this, what did you want to do next? You knew that the heat was coming from the electrode. What did you want to do next?
The next thing is, it was claimed that it's of nuclear origin. So one would think of what would be the simplest measure, the simplest approach to prove that this is indeed in nuclear origin. Well, people in the very first, since that was due to deuterium present in the palladium, people assumed that the reaction is D plus D goes to tritium, goes to helium, and so on. So if this is the case, that one would expect to find tritium in the escaping gases. Well, why did we select tritium? Well, for 2 reasons. It's the easiest to measure, the simplest equipment. You don't need very much of equipment. So what we have done first, we sent, since we didn't have equipment in-house, we sent the samples to Utah, and Flashman and Pants, or one of the students there, did make the analysis and reported excess tritium. Well, we weren't very happy with it, so we sent another one to SRI. McCoury then sent that back. Again, we showed excess tritium. The results were, the numbers were not exactly the same, but both laboratories showed that we did have an excess tritium. That means we kind of synthesize, well, we do know that at least there is a evidence that this is a nuclear process.
Okay.
Well, but there was another one which we could have done, and we have done it. If there is a nuclear process, there must be radiation coming out. And the simplest one would be, again, to use normal photographic film to see whether we get any image. Well, as a matter of fact, we did. And so at that point, we're quite happy. Qualitatively, we convince ourselves that the process is working. That means co-deposition is one of the techniques that one can use. that it is of nuclear, the heat, excess heat is of nuclear origin. So then the next problem would be to try to do it quantitatively, to see whether we can get some numbers. And at that time, as you know, we have got the state-of-the-art equipment to measure tritium content, and we spent about a couple of years to do that, and we convinced ourselves that yes, indeed, we have tritium production, that there are periods in which the tritium is very highly. We calculated that we produce about 10 to the third to 10 to the fourth atoms per second. But at that point, the problem was still, why do they have the incubation period? Incubation period in massive electrodes. That means using Fleischmann and Pans procedure. You have to wait between completion of your charging and onset of the nuclear events, and that time is unspecified. It could be days, it could be weeks. So now the problem is, what is happening in meantime? So that for the next few years, our emphasis was on trying to learn something about the process itself.
Okay. You've mentioned a couple of times that it was nuclear in origin, and you convinced yourself it was nuclear. Why is that important?
Well, important for one simple reason. If it is of nuclear origin, you enter a completely new area of investigation. After all, nuclear reaction should not happen at room temperature. So if it did happen, that opens the whole new area of research, of interest to physicists. What is happening there?
Okay, and also, if it's nuclear, the chances of a lot more energy being involved and being available.
Yes, well, that is another thing. The question on the problem was, if we have enormous amount of energy, we can use it. The difficulty here is that this is a low-grade energy, because the best we can do in normal circumstances would be about 100 degrees centigrade to get that heat out of the cell. Now, if we want to go to molten salts and so on, then we can go higher. But using the Fleischmann-Pans procedure, the best we can hope is around 100 degrees. That means we can still, the usable range would be around 70 degrees. And 70 degrees, according to Fleischmann estimates, is about a great deal, about 50% of total energy use is below, at the temperatures below 70. If you are talking about heating and all that sort of thing.
When you say 70, you're talking about 70 degrees centigrade,
yes,
which
course,
is
yes.
150 degrees Fahrenheit or something like
well,
that.
I still like that.
So you could certainly heat your house and heat your water and things like
Yes,
that with that energy device at that level.
Yeah.
Okay, now tell me some of the other experiments that you did in order to try and understand what was going on. I know you did some experiments in cyclic voltammetry. Can you describe those?
Well, no, this is, well, there is a number of procedures that if you wanted to, well, the cyclic voltammetry is one of the techniques that people use to understand the kinetics of the reaction. In our case, it suggested that one of the species that is in the electrode is a complex called molecule ion, D2+. That means two deuterons with one positive charge on it. So that was but outside of that, we did get some understanding of the system itself, but nothing that would lead to, well, it would come a little bit later, perhaps we'll make use of it.
Okay, so was it a way to measure the loading that you were getting?
Oh, that is a different technique again.
Okay, can you describe that?
Well, You can measure loading ratio by simply putting anodic current. So in other words, you have a sample, you believe it's saturated or it contains now deuterium in it. If you reverse the current, that means put so-called anodic current on, then the potential will go varying until it gets to some steady state, which will tell you that you don't have any more deuterium in the system. And from the amount you can calculate. And turns out that in co-deposition, under normal circumstances, you are getting more than the ratio of V to PD is more than 1. And for the Fleischmann-Panz effect to occur, you need at least 1, ratio of 1. So there's another evidence that if you really wanted to have some high reproducible results, you use co-deposition.
Okay, so now we have a co-deposition technique where
Yes.
we have measured, we've seen X-rays, we've seen tritium.
Mhm.
Can I go back a step? You started talking about that. You mentioned that now you have something that's reproducible. I'm curious if you could go into that just a little bit. Like, when was that,
Yeah.
and what was the significance of that?
Yeah, let's go back. Yeah, from the very beginning, you said that you were lucky or whatever, but in any event, the very first time you tried the co-deposition technique, it worked.
Yeah.
And it worked quickly,
Yeah.
in a matter of minutes instead of a matter of days or weeks.
Yeah.
Did it work like that every time, or was it very
Every single
repeatable?
time. This is one beauty of it, that this is reproducible. Now, why is reproducible? That's entirely different story now again. Because in here, we know what we have. If you buy massive palladium, the metallurgy of it is awfully complex. You really don't know what you have. It turns out that only certain kinds of palladium were the useful ones. And those ones from some company, I don't remember the name, Matthews,
Johnson.
something like that. Now, in the co-deposition, you can control, and each time you have the same situation. If you control your current and your solution composition, you will have always the same thing. So the material itself is reproducible, and then it comes also that the effect is reproducible.
So now you have addressed another one of the big issues of the skeptics, which was it isn't reproducible.
Well, we address essentially two from our measurements. Not only that it is reversible, is reproducible, but also is more effective than the use of massive electrodes. The degree of variance differ in very poor experiments, which we consider poor. We still get about 40% excess power. How high we can go, I really don't know, because we have never tried to optimize that. To do that, you are getting into the engineering aspects of it. And to do that, you need money. And if you don't have money...
Let's talk about the money. Who has funded all of this? You've been working on this now for 18 years? 19 years?
Well, the first year we've got from IR, I think, 1 man-year level.
Okay, so the laboratory itself
A laboratory
used internal
itself,
funds
yes.
and provided one work
And
year.
then there was nothing coming out until when you got personally involved in it.
Okay.
So that was then again on the level of what, 1 man year or something of that kind. So essentially we did not have any support. My time I was on overhead, and in those days, since I was near retirement, really didn't matter very much. And I had, well, as you know, the situation is very unpleasant to people which are
If you're on overhead, it's not comfortable.
yes, and but somehow I managed for I don't know 3 years, I think.
Okay.
It was that I.
And I was gone during part of that time,
Yes,
wasn't
you were.
I? I was in
And-
another organization.
Yes, and at that time, remember, I had a formal support of I don't know what 1 year, I think. And after that, I have retired. So it was some kind of a pause in our activities in the lab until the year of what 1999,
Mm-hmm.
when you re-invited me to join the effort, and from that time on, we have completely different story. And as a matter of fact, at that time we really start learning and doing something very exciting and very useful.
So, from 1999 on, tell us about the working relationship. I know you come to work early every morning.
Well, yeah, my working hours are very short, between 7 and 9. Those are my normal working hours. Well, at that time there was a problem. Within this time that I was in retirement, I was sometime wondering what is really happening, what can we do to what other people have not done yet. So one of the idea was to see whether we can change the so-called input variables. In other words, I visualize the whole system as a chemical reactor of a kind. So to understand what's happening, I like to know what's going into it and what's getting out of it. And by knowing these two, I can pretty much guess what is happening inside of this box, or whatever you want to call it. So one of the things that we thought might be very useful would be to introduce another input variable, and in this particular case I was thinking of using an electrostatic potential. Now there was a reason for it. We believe that the rate of reaction depends very much on a number of dislocations, defects that you have in the structure itself. These defects are produced by motion of deuterium inside, because you have stresses, all sorts of things. Now, we did know, and this is very well known, that if you take a small particle, say something on the order of a micron, and put in electric field, that it will change shape. By changing shape, you are going to produce additional defects in it. And if this is the case, then we should have a higher output. Well, that's what we expected. Now, I don't know whether we got higher output because we never measured it. But what we didn't expect was that there are going to be some violent reactions. And when we look at the sample, we saw that it no longer looks the way the co-deposited film should look like. It looked completely different, even to naked eye. So we went and looked under SEM and found that there are distinct spots there, which looks like the metal was melted and then solidified under the liquid. And so we thought, well, why don't we analyze the situation? That means is try to make a surface analysis. And to our surprise, we found new elements formed, those elements which were not there originally. So now there is another proof that some sort of a nuclear event has taken place. Now, why did I say that we thought that it looks like solidification of molten material. Years before, sometimes in our second or third year, we had a thermal runaway in our course of measurements of our tritium. No, was it tritium? I think it was tritium. The temperature of the electrode became so high that it essentially melted and deposited on the walls of the cell. And at that time, we reported that thing very nicely. You can find that in the Physics Letters journal. So now we have another thing. We have a new branch, new type of nuclear reactions that does occur. If you change the input variable, put another one on, you will have rather unusual effects. Mm-hmm. Well, that again, then we spent some time to try to see whether this is reproducible or not, and we found yes, it is reproducible. So following that, one would ask, well, why don't we use now magnetic field and see what happens? Well, the situation, the morphology of the film, of the PD, is quite different. Now the globules, which were spherical, look now like flattened. And what's more, the new elements that we are finding or seeing are uniformly distributed throughout the electrode's surface. That is the essential difference between the electrostatic field and magnetostatic field. So there must be some difference in action between how the electric field interacts with the system and how the magnetic field interacts with the system. Now, of course, is how do they react? How do they interact? So the most recent thing, which you are not aware of yet, but you will soon be aware of, we have done an experiment in which we see that, among other things, the effect of external magnetic field is that of collapsing or trying to squeeze the clusters, the iron. Now, you have to, I didn't mention one thing, which in my opinion is the crucial experiment that we have performed. That was the IR imaging of the electrode surface. You can see that there are so-called hotspots formed. Now, very few people did appreciate the importance of this little finding, except of course for Flashman, which made a point of it during the meeting, I think in Japan, and whenever they had there. And then of course was a rather, people start thinking. Now, what do these things do mean? They simply mean one thing, that we have some way of rationalizing what is happening inside. Since we know that there are new structure formed, and since we know where the system is, that the system is not in equilibrium, but far from equilibrium, that there is exchange of energy and mass between the system and the environment. That means that at least we have methods by which we can analyze, that is the use of the irreversible thermodynamics. And well, this is still the area which very much interests me, but I don't do too much about it at this time. So that's about where we are today.
Okay. But you've talked about the different morphology between the electrostatic field and the magnetic field. Can you describe a little bit, was there a difference also in the elements that were formed and the transmutation that occurred?
I cannot say that with certainty. There seems to be that in the electrostatic field we see elements like magnesium, aluminum, zinc, and in magnetic field, in addition to that, we see iron and chromium. Now, whether this is, I don't think that I have enough data to make a positive, make clear statement. It seems to be some difference, but
Okay. You published this in a refereed peer-reviewed journal, is that correct?
yes, that's
Okay. The biggest complaint that the reviewers had was, well, this is just contamination. Can you, how did you convince yourself and ultimately the reviewers that it wasn't contamination?
well. If you have an amount, if you have, let's say, a single element you see, and there are places, there are situations in which you see single element, like for example calcium, and it turns out to be 100%. Now, if you have that high concentration, it's hardly possible that it came from. Secondly, we know what we are putting in. We know what is the purity of palladium chloride. We know what is the purity of heavy water. We know all these things. So if they are not there and we see them on the surface, they had to be. Now, the arguments which people again are coming back to the massive electrodes. Very rarely you have 100% palladium. You have perhaps 99.999%, but you still have some additional elements. It could be almost anything. Now, the argument, some people say that if you do that and carry your experiments for about a month, that there is chance that they can come to the surface. I don't know how, but some people say they can, and collect in some places. Now, against this argument, remember, our experiments we carry our experiment within days. So this magic transport to the surface is out of question. You cannot transport something you don't have to start with, and you cannot transport something with a very slow process in short period of time. So,
Excuse me. Isn't there another factor with aluminum that was showing up on the surface, that if you could not plate aluminum out of the aqueous solution?
oh yeah, well, there's not only aluminum, magnesium, silicon, and others. You cannot plate it out. In other words, some people were arguing, well, perhaps these impurities came from solution. Well, we already decided that they cannot, because we know what is heavy water does not contain these things. Although some people say, well, it might. Well, I doubt it very much. But if it does, certainly cannot. You'd have to have some Maxwell demon there to pick it up and say, go there to that particular place. In other words, if that came from the solution, would be uniformly all over the surface.
And it would have violated Maxwell's law.
The Maxwell demon would be asleep, I suppose.
Okay, details.